All right, section 2.1. I'm going to try something new this section and for chapter 2, and I'm going to try to do a summary lesson. And so there will be a formal lesson, and then there will be the kind of summary, the shortcuts, the simple mode, if you will. And so first off, for 2.1, we're talking about tangent lines and rates of change. And so I want you to tap into your previous knowledge and remember that in Algebra 1, we did something like this. And in Algebra 1, this M represented what we called slope. And in fact, that's what we're dealing with when we talk about rates of change. Slope is going to be what we refer to as rate of change. So in Algebra 1, we used words like up 2 over 1, up 5 over 1, down 2, down, So those are the words we used in Algebra 1 and Algebra 2. And now in Calc, we're going to call slope, and we're going to say that that's the equivalent to rate of change. Okay? So tapping into that prior knowledge, we used to do slope as rise over run. And you could calculate it like this, given any two ordered pairs. And remember, an ordered pair for this graph, it had to be on the point, like on the graph. So if it was a line, it traveled through the point x1, y1, or x2, y2, right? Connecting those dots. Now it becomes important because when we're talking about what we already know, we want to convert what we already knew as like mashed bananas into whole bananas. So all we're going to do is kick it up a notch, and we're going to change the word slope to rate of change. And we're going to use a slightly different notation, but it's exactly the same concept. And so what we want to talk about right now is our favorite curve ever in calculus, f of x equals x squared. And keep in mind that we're going to only look at the first quadrant there, where x is greater than or equal to 0. So I'm going to plot a couple of points. And I'm doing this by simply plugging in these x values. So I'm just labeling them because I'm going to use them. And so if I chose any 2 points on the graph, let's say I'm going to mark some lines on here. From this point to this point, you can see that tangent line, and from this point to this point, and from this point to this point. And so if you just look at this generally speaking right now, just looking in general terms, one of the things you're going to notice is that the slope of that line is not constant. Okay? So Algebra 1 idea of just having a straight line is not going to work. So what we have right here is we have a secant slope. This right here is a secant slope. Okay? Secant is just a line drawn between any 2 points. What we want, and this is the difference, we want to see what the exact slope of the tangent line is at a point. So at a point here, at a point here, at a point here, at a point here, okay? And I just chose those points as arbitrary points. I could have drawn it anywhere on the curve. And what you can see is as that graph, as the point changes on that graph, the slope of the tangent line is also changing on that graph. And so it's really important that you see that, okay, we have a secant line, which is kind of like Algebra 1-ish, but now we're going to change it to the slope of the tangent line. So you can see that at 0, it appears to be a horizontal line, slightly positive, more positive, more positive. And so the slope of that tangent line is increasing as we go from 0 to 3. Okay? And so if I want to find the slope of the tangent line at any point to the graph, then I need to have an equation. And so what I'm doing now is I'm actually going to use the limiting process. It's why we do limits in Chapter 1. It's why we do limits in pre-calc. And the reason is everything in calculus is going to boil down to a limiting process. And so what I want to do is I want to say, hey, let's say I want to find the slope of the tangent line at x equals 1. So I need an equation to find the slope of that tangent line. And so what I want to do is I want to say, okay, well, what if I started with this dot? So the slope between those two. And then what if I took the slope between those two? And then what if I took the slope between those two, and then between those two, and then between those two? And what happens is, as I move this dot closer and closer to the point that I want it to be at, I can see that, oh, I'm going to get a much better approximation of the slope of the tangent line to the curve at x equals 1. And so, hey, if I took this ordered pair right here, okay, and for any ordered pair, that's what it's going to be. And then let's say I move some distance over here, and I put another dot right here. Well, this distance here, this horizontal distance, I'm going to go ahead and call h, which means this ordered pair as an ordered pair of f of x plus h for the y value and x plus h for my input. Remember, I'm starting here and I'm saying this is x and I'm moving the horizontal distance h. So right here, this is some x plus h, where h is the distance away from my actual dot, okay? And so you can see here, if I'm bringing this dot closer and closer and closer, if I'm moving this dot closer and closer and closer, what's happening to the value of h? What's happening to the value of h? Go ahead, say it. Ms. Collins, it's approaching 0. Yes, that's the idea. So the first way I want to look at it is, let's say h is going to go to 0. And then I want to find the slope of that line. The change in the y's over the change in the x's. And, oh, what? Ms. Collins, that looks so familiar. I know. You should recognize this, okay? You should recognize this as the, say it, DQ, not Dairy Queen, difference quotient. There it is. And that's going to be true for any 2 points. So let's just check it. So I want to see what's going to happen at the point 1, 1. Okay? So I want to find the slope of the tangent line at 1, 1. Now, I will tell you this right now. This should be a review because that is your difference quotient. Okay? And if I do it the long way, remember that f of x was equal to x squared. So f of x plus h is equal to the quantity x plus h squared. And if we do this, x squared plus 2xh plus h squared. I'm not going to show that out. You guys know how to do that at this point. And so now I want to use my notation. The limit as h goes to 0 of x squared plus 2xh plus h squared. That is the f of x plus h, x squared, all over h. Now, if I've done this correctly, everything that comes after this minus sign should go away. If I haven't done it correctly, something's left, okay? So the entire original function, in this case x squared, should be gone, in which case I'm left with 2xh plus h squared all over h, which we can simplify. Still can't plug in 0, so I'm still doing algebra. And now the limit as h goes to 0 of 2x plus h is equal to 2x. Okay, your book calls this the slope of the tangent line. This is one option for the slope of the tangent line. In this case, this is the example we just did. M tangent, that's the slope of the tangent line. And now, the good news is, this right here is an equation. So if I wanted to define the slope at any point on the original curve, y equals f of x, which is equal to x squared, I could just plug in an x value. So at x equals 1, the slope of the tangent would be 2. At x equals 2, the slope of the tangent line would be 4. At x equals a gazillion, the slope of the tangent line is 2 gazillion. So it works for any values of x. So this is the limiting process. And the limiting process, the first time we use it, is just to calculate function values, or the limits. What's the function doing? The second time we use it, we need to understand limiting because we use the limiting process to find the slope of the tangent line. Now, there is more than one way to do this. And so the second way we can do it is to actually have the function value. and to just find what the slope of the line is at a value close to that point. For example, we're going to use the same curve, and we're going to do the exact same thing. Okay, so let me remind you, back here, scroll down. At x equals 1, the slope of the tangent line would be equal to 2. Agreed? So what I would do is I would take 1, I would plug it in here, and I would get this, 2. So now option number 2 is to say, hey, what's the slope of the tangent line to this curve at x equals 1? Okay, well, let's do a little bit of thinking. If x is equal to 1, what's f of 1? Good answer, 1. All right, so 1 squared is 1. And then I say, okay, well, if I want to look at the secant slope, that would be between any 2 points. Noting that the first point is at x comma x squared, and the second point is at 1 comma 1. And that would give me a secant slope. And in fact, I could do a little bit more math on this. We love you, Algebra 1. And I could get rid of that, and I could say, okay, well, that's the slope of the secant line. But here's the difference. We want to find out what happens as we get really, 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 really close to 1 without actually being there. So we say, hey, let's let the limit of x go to 1. And we want to talk about what happens to the slope as that secant slope gets really, really, really close to 1. Now, let me just go back to my picture for a second, because here we are. The red is the secant slope, correct? And so what I want to do is I want to take a look at these black lines and say, okay, I was starting at 3, and now I'm at 2, and now I'm getting closer and closer. And so what's happening, remember, these black lines, as I bring these dots closer, the secant slope approximates the tangent slope. So now, here I am, and notice the only difference here is my limit. I'm not talking about a distance from x. I'm saying I want x to go to 1. And remember, that distance has to be infinitely close to 1. So I say, okay, I'm going to do the same thing I did up here. I'm going to say, let's do this. And I can't plug in 1 here. I can't plug in 1 here, but I can do some algebra, and I can get rid of it. And so now, guess what? Now, magic math, awesome factoring, x plus 1. Can I plug in 1 now? Yes. What's 1 plus 1? 2. I'm getting the exact same answer that I got the first time. Let's go back. Let me remind you. We did it the first time, and we got this. 2. And now we did it again, and guess what we're going to get? 2. Yay! We are happy. Okay? So really, all we're going to do is use the limiting process to find the slope of the tangent line. And we can do that using any 2 points. In this case, I used a very specific point. Okay? In the previous example, I used arbitrary distance, h. So some distance away from, okay? That second point was f of x plus h. I could very well have called it f of x2, f of x5, f of x whatever. So regardless of what the notation says, the idea is that you're finding the limit as you approach that second dot really, 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 really close to the one you want, okay? So let's take a look at some notation. These are the options. Okay, so the first one, again, all of these are going to give us the slope of the tangent line. Okay, this one, number 2, looks the most familiar to you. It is extremely important here that you notice this x naught is the second point, the value that I want, so to speak. X is arbitrary. That's just telling me that I'm dealing with x. That's the thing I'm changing. That's the input. X naught is where I am looking. Okay? So if I'm looking at x equals 1, which we just did, then I would plug in 1. If I'm looking at 2, then I would plug in 2. So for example, we just did this example, 1, change that to 1, change that to 1. You could just as easily have done, hey, I want to look at 2. I want to look at 2. I want to look at 2. Okay? So any value, x naught is the place I am looking at. That's where am I looking. The third option that you're going to see in the fourth option, those are very specific, very specific, my bad, and those are going to be related to velocity. So I need to point out two things here, and then we'll move on. When we're talking about velocity, velocity has to do with a change in position per time. And so notice here we've changed the x's to t's. That's the only difference, okay? That is the only difference. And the difference between average and instantaneous is the same thing as saying secant versus tangent. Okay? So notice what's missing. The piece that's missing here is this. So with the secant slope, we didn't take the limit. We used the limit for the tangent slope. And that's what you have right there in front of you. Okay? So now what we're going to do, your book is then going to convert. And this is just notation. I want you to see that it's exactly the same. Average is a secant. That's a general picture. Instantaneous is a tangent slope. Okay? So a rate of change is another way of saying slope. Okay? So what we want to do now is take a look at a couple of examples. And so straight out of your book, go ahead and grab your book right now. You should have this at home while you're listening to this. I'm opening mine right now. Page 141. Look, I'm even turning the page. Page 141, number 12. Okay, page 141, number 12. This is what I'm given. Hey, look at this. Looks pretty close to what we already have. And I'm told that x naught is equal to 1, and x sub 1 is equal to 2. And I'm told to do a couple of things. It says the function y equals f of x. I'm reading the directions now. And values of x naught and x1 are given. Find the average change of y with respect to x over the interval. So change of y with respect to x. That right there is going to become what we use as the derivative. But for right now, what they're really saying is find m, the change in y with respect to x. That's what we're really doing, okay? This is what those words mean. Slope of tangent and or secant line, okay? So that's all we're doing. We're just finding the slope. It's a lot wordier, but it's not going to matter. And now the important thing to note here is on part A, they're telling me the average rate of change. So if you look back on your previous slide, you'll see that the average rate of change is f of x plus h minus f of x all over x plus h minus, my bad, no f on that one, x. And so remember, I could change them to t's, and that would work just as well. This is given an x, so I'm going to keep it to x. And so I need to choose 2 points. And, oh, wait, look, they gave them to me. And so now all I'm going to do is find the average rate of change between those 2 points. So this is just algebra 1. So 2 minus, oh, my bad. 2 minus 1 goes on bottom. Now, how do I figure out what's going to go here and here? How do I find out what f of 2 is and what f of 1 is? Hint, hint, hint. Plug it into the original equation. So I'm going to get 1 and 8. So I'm going to come over here and I'm going to go 8, 1, and I'm going to get 7 over 1, which is 7. Okay, that is the secant slope referring. That is the secant slope. Okay, that is the average rate of change. Now it says to find the instantaneous rate of change, which your book will note as this. Okay, same thing. notice the only difference is the t and the 8 and the x. But here's the big difference. The big difference between average and instantaneous is the limiting process. And so now we have to work in general terms. So the first dot is going to be x comma x cubed. And the second dot, according to this, it says find the instantaneous rate of change of y at x naught. Well, x naught was given as 1. So that would be 1 comma 1. So I want to take the limit as h goes to 0 of x cubed. And I don't know what it is, right? I don't know how far away it is, but I know it's at x cubed, whatever it is. And then minus 1, because that is the value, and then over h here. And so I say, well, wait a second, how's that going to work? Because what do I have to plug in here? And what do I have to plug in here? So can't combine both methods. So what I need to do is I need to say, oh yeah, if I'm doing this one, then this has to be this. Correct? And then this is just h. Now, what I'm going to do is I'm going to end up plugging in 1 at the very end. Now, this I'm going to show you. I'm going to do it this way because that's the way the book is going to do it. And then I'm going to show you the other way where I can actually use this method. Okay? So I say, okay, this one doesn't work because this doesn't make sense. But here it works. So let's see what happens. H goes to 0. So 1, 3, 3, 1. X cubed, x squared, x. I'm using Pascal's triangle because that's easier for me. H squared, h, and plus, and plus, and plus. And then I'm going to minus the x cubed. If you don't remember Pascal's triangle, yes, you are going to have to expand that. Okay, you can do that on the side if you need to. And then that's all over h. I still cannot plug in h equals 0, so get rid of everything I can and see if I can simplify. I notice that there's a common factor in all three of those. And now I can plug in 0. And if I plug in 0, that goes to 0, and that goes to 0. I'm left with an equation, 3x squared. Now, according to the question, it said to evaluate this line means to evaluate at, x naught equals 1. And my answer is going to be 3. Okay, now I started this up here, and I want to show you. If I come to right here, even though your book has a different equation for r instantaneous, I want to show you that it doesn't matter. It told me to look at the average, look at the instantaneous rate of change as x was approaching 1. That would be your x naught. And the original function was x. So that's what we have. And now you say, well, that doesn't help me, Miss Collins. Well, it does, because let me remind you, this is a factoring problem from Algebra 2 and or pre-calc and or regular pre-calc, honors pre-calc. 1, 0, 0, negative 1. I take the bottom, I flip the number, I'm going to do a little synthetic division, and I end up with x squared plus x plus 1. And so the top of this actually factors to x minus 1, x squared plus x plus 1, all over x minus 1. And remember, the very first thing I'm checking is, can I plug it in? And the answer is no. Can I plug it in? Yes, now I can plug in. When I plug in 1, the limit as x approaches 1 of x squared plus x plus 1, plug in 1 plus 1 plus 1, and you get 3. Look, the notation is different. This equation right here looks different than this equation right here, but guess what? The answers are exactly the same. So this is really important to me. It does not matter to me which method you choose to use, okay? You're going to get the same answer. Regardless of method, I need to see work. I need to see that you are setting up an equation. I need to see that you are simplifying. I need to see that you're following limiting rules and you're not just substituting willy-nilly. You need to be able to show me your steps, okay? For part C, find the instantaneous rate of change of y with respect to the arbitrary value of x naught. Arbitrary just means in general with any x, and that's what we're talking about, okay? That's what we're talking about. And then I could plug in any x naught, okay? I don't need to rework it, but that's what we're talking about. We're talking about arbitrary values, means if f of x is this, then f of x naught is that, correct? And f of x naught plus h is equal to x naught plus h quantity cubed. The notation just starts to look uglier. Please, please, please keep in mind that you're going to get this. That's equal to this. Instantaneous, need an N in there, Ms. Collins. Which is going to be equal to whichever form you want to use, okay? And in this example, we're going to get the answer of 3. Now, the part D does require a little bit of understanding because it says the average rate of change in part A is the slope of a certain secant line. The instantaneous is the slope of a certain tangent line. Sketch those. Okay, so here's, oh, my bad, I need to scroll down. So here's what I want you to see. I want you to see this. Remember, we were doing x cubed, so that looks like this. Y equals x cubed. Okay, so between 1 and 2. Between 1 and 2. This was 1 comma 1, and this was 2 comma 8. This is the secant slope. This is the average rate of change, okay? The second line you should have drawn, and I kind of want this one to be a little more straight, so I'm going to use that. There, that is going to be my, that is my tangent slope, or my r instantaneous, okay? Now look at the difference between the slope of the black line and the slope of the red line, okay? So that's what we're talking about. The average is between any 2 points, and it doesn't matter. It's just a straight line. The slope of the tangent line, or the instantaneous rate of change, is going to be what happens when I move this infinitely close, okay? Let's do one more together. Okay, page 141, number 16. So let's scroll down to number 16, and you are told y equals x squared plus 3x plus 2. And in fact, you're given f of x. And you're told to look at the point x naught equals 2. And you're told to find a formula for the slope of the tangent line. Now, a formula for the slope of the tangent line is going to be in terms of x. It'll be like an equation. And so what I want to do is say, okay, well, let's look at the limit as h goes to 0, because I need an equation. And so that's going to be f of x plus h minus f of x all over h. This is going to be the one your book refers to when they start talking about an arbitrary x. Arbitrary x. All right, so f of x plus h. And that means we're going to plug in anywhere we see that. We're going to plug in that. And so f of x plus h, this is going to look a little ugly, but that's okay. X squared plus 2xh plus h squared plus 3x plus 3h plus 2. This is all f of x plus h minus f of x, which is x squared plus 3x plus 2, all over h. And again, we're looking at the limit as h goes to 0. So can I plug in 0 yet? No, I cannot. But I can get rid of x squared plus 3x plus 2, x squared plus 3x plus 2, gone. And now left on top, I have, I'll just rewrite it so we can all see it. That's what I have left on top. Can I plug in 0 yet? Some of you are saying yes because you're already simplifying, but that's okay. I'm going to write it out. So here we go. FYI, I'm hoping that you are trying to do this as I do it, simply because I think it's good practice to see if our work matches up. While you're working, you can be looking up to check. I'm going to cross those out, and now I can plug in h equals 0. As I plug in h equals 0, this becomes 2x plus 3. Okay, this is the slope of the tangent line. And that's going to be valid at any arbitrary x. Your book likes to throw in the x naught idea. I don't need to. That's just notation nonsense. Okay? More concerned about the process. That you understand when they're talking about an arbitrary x, that this is what you're looking at. Okay? So it's an equation. That's going to give me the slope of the tangent line. And now it says use the formula to find the slope at the given value of x. Well, for part B, it's telling me that x naught was equal to 2. So 2x plus 3 evaluated at x equals 2 is going to give me a slope of 7. Ta-da! Okay, that's the answer. All right, so what you're going to do now, I'm going to let you try one on your own, and then I'm going to work it, but then I'm going to stop the tape. So I don't want you to listen to me do it. I want you to do it, and then I'm going to talk through it after. Example 3, page 142, number 22. This is actually a word problem. A 50-foot horizontal metal beam is supported on either end by concrete pillars, and a weight is placed in the middle of the beam. If f of x models how many inches the center of the beam sags when the weight measures x tons, then then the units of rate of change of y equals f of x with respect to x are inches per ton. So you're looking at number 22, and according to number 22, you just need to tell me if that's true or false. That's all you're going to do, is tell me if that is true or false. Okay? So maybe draw a picture, maybe see what's happening, and then I want you to look at that in terms of just looking at the units. Okay? All right, that's it for today. We also have the additional lesson posted by Mr. Clinton, and that will have further information. All right? Good luck.